Welcome back, everyone. Our next talk is by Zafer Esen on sound and complete invariant-based heap encodings. Thank you very much for being here.
Yep, thank you for the introduction. So this is a joint work with Philip Brummer and Shark from the university, and Philip is from Regensburg, and I'm Zafer. And I will explain what I mean by sound and complete, because these words can be overloaded, and also invariant-based heap encodings. So just to give some background, what I mean by heap, I mean heap allocated data structures. So like these are, for example, linked lists, trees, and people don't often use this because they are flexible, right? You can change their structure during runtime, and their sizes can change. You can allocate new nodes, and yeah, I guess everyone is familiar for this. But these are quite challenging for verification. I mean, this is not a new challenge. Many people have been working on these for many years now, and there are many approaches which I won't go into, such as shape analysis and separation logic and others. And the challenge is because, well, there's first the memory safe errors, and these are mainly showing up in languages that are not memory safe. So if you use Java or another memory safe language, you can get some guarantees, but if you stick to the safe parts of the language, but in languages like C, C++, you still have to deal with this. And another thing is that these can be unbounded, right? Until the runtime, we don't really know the size of these. So you need to deal with these unbounded sizes. And we want to, I mean, the context I'm talking is automated verifications, and the properties will be often quantified. So you want to express some property that all nodes of this list has some, for example, value or something like that. So you will have to deal with quantifiers. And when you are doing automated verification, you have to come up possibly with quantified invariants, which is much more challenging than non-quantified ones. So when I talk about properties, I will be talking about two properties. One is memory safety. As I said, these are such as invalid pointer accesses and no memory leaks, no double freeing of memory, and the functional correctness ones. And the functional correctness one is maybe more interesting if you are working in a memory safe language, such as saying the list is sorted, or the maximum value in the list is in the tree is some value. And then you have to reason with this through the heap. So you put the list on the heap, you have to do some heap reasoning to prove this property. So how does this relate to the WG3 objectives? One relation is that this is in the context of automated verification of programs with heaps. And to be able to do this, we mainly work in constraint horn clauses. So we try to come up with the invariants automatically. And yeah, if you want to we just give the specification, okay, this list must be sorted. And then we want to show this automatically. And then unlike deductive verification, for example, in pharmacy, you specify the invariants. And there are some plugins that try to refer to automatic as well, but here we try to not give any loop invariants, nothing like just this property to be verified, and then the tool tries to infer the invariants so that program is verified in that. And we also implement the approach in a verification tool and compare it to other approaches used in SPCOM to deal with heaps. And I was reading a book recently, and I saw this. So our approach will be program transformation. We will take a program and specification and transform into another program. And I came across this, that program transformation is a hot topic these days, many advocated using. And this was from the book. Apparently it was a hot topic in 1981. And it seems to be making a comeback, but I mean, the context is a bit different now, how we are doing these transformations. So in this work, we take a program with heaps plus its specification, and the program is P, and we turn this into another program P that is easier for automatic verification, hopefully. Not always, so experiments will show that. And we talk about soundness of a program transformation. That means that if the transform program is safe, then the original program was indeed safe, or by contrapositive, you have the original program is unsafe, then you actually find the bug. And by completeness of a program transformation, we mean the other direction. If the original program is safe, then the transform program must also be safe. So this is what we mean by soundness and completeness in this work. And we are using, this is a bit more background, we will use constraint horn clauses. So you can think of this as an extension of SMT, if you are familiar with that, where we leave some uninterpreted relation symbols. I will show some example of that. So we take a program plus a specification, and we have some tool that's like the first arrow, for example, Tricera is a tool that we are developing. There's C-horn, and these tools produce constraint horn clauses. So they represent the program and the specification in logic. And then there are off-the-shelf horn solvers, such as Alderica, Golem, Spacer. These, like SMT solvers, they give us a result, hopefully, safe or unsafe. They can also time out, of course. And if you get a safe, the solution includes the invariance that we want to infer. So loop invariance. You can also infer function contracts. All of these are like program invariance in the encoding. So once you get a solution, you have inferred them. One thing to note is that the inferred invariants are not always the weakest. So like if you are trying to infer the weakest invariants, these might not work for you. So let's look at an example, how we go from a program into a constraint horn clauses. So very simple program. So the start here is a non-deterministic value. So we have some x is assigned non-det value. And then while x is positive, I decrement it. And at the end, my properties. So there's no heap here, just a very simple example to understand horn clauses. And I think we have time. Feel free to interrupt me if something is unclear. Yeah.
And x be negative?
Good question. So this program is actually unsafe. So for it to be safe, x must be positive, right? And in the tools that we are developing, we don't really check for termination. So if here x is negative and you encode it using mathematical integers, this won't even terminate, right? But yeah, let's look at how one could encode this. Like, don't think about if it's safe or not for now. So what we do is we associate each program location with a label, and these will be the program invariants at those locations. So if you work with for logic, you could think of these as predicate symbols, and the predicates will characterize a set of states possible at those program locations. And these will have as arguments all the program variables. So here only we have x. And we can encode this in horn clauses then as follows. So we start from true. We don't have any precondition or anything. And then that implies that this first location, because we didn't assign, like, for example, we didn't say x is positive here. If x was constrained to be positive, we could have said instead of true, x is positive implies I1x. And then this program would have been safe, actually. And then in the second clause, we see that, so this left-looking arrows are implications. So this is in logic, and all the clauses are implicitly universally quantified. So we have for all x, I1x is implied by true, and so on and so forth. And you see, for the while loop, we have I1x to I2, and then from I2, we go back to I1. And here you have a loop. So the nice thing about this is that if you have loops, like if you were to try to encode this in SMT, you would have to find the loop invariant first. But here we don't have to find the loop invariant. I1 is the loop invariant. We just leave it symbolic. And then if the horn solver can find a solution to this, such as Alderica, Golem, Spacer, it will give us these interpretations for these invariants. So for example, if this was safe, then you would have I2 is x is greater than 0. But of course, this will be unsafe. And a counterexample to this would be if you set x to -1, you fail this assertion, so you don't execute this. So a constraint horn clause is just the first order formula, and we have this head and some constraint and body literals. And we often write this in Prolog. The syntax, it's not too important. I won't talk much more about horn clauses, just that that's the context, like we are going from programs to horn clauses. And now the issue is when you have programs with heaps, so we have theories like in SMT, like we have arithmetic arrays and things like that, but we did not have any support for heaps before. So you use other theories to encode heaps. You basically eliminate them when you are going from programs to horn clauses. And for this, one can use array-based encodings or invariant-based encodings. So this was in the literature. I will talk about, give some examples of invariant-based encoding. And there are also other ways possible here as well. And one problem with that is that you are losing the heap structure. So once you go to the horn clauses, you no longer have an explicit heap. So if you want to reason about heap, and if you're, for example, encoding, the invariant-based encodings in literature, they weren't complete in the sense that I defined completeness. So you are starting with the program and then you have an encoding that is not complete. That is, if your tool says that your program is unsafe, it might not actually be unsafe. And we tried to address this first. And for this, we introduced the theory of heaps. This is prior work. And now you have a way of specifying heap operations, such as allocation, like similar to arrays, like you can read locations and write locations. And what this allows is that in the constraints of our horn clauses, we have now heap operations. So you don't really lose information while going to the constraint horn clauses. Therefore, you can encode them at the level of horn clauses now. And since you have a logical representation for heaps, you don't really end up being incomplete, even if you apply an incomplete method. But of course, you have to now deal with these heap constraints, which is just as challenging. It's you cannot avoid that. We just moved the problem from the front end to the solvers now. So yeah, we start with some program with heap. We apply this theory of heaps transformation, and we end up with horn clauses plus heaps. Now, this original space invariance approach, it took Java programs. It was in the context of some tool that's called JHorn that took Java programs and transformed them into horn clauses. And it only used standard theories. We had a paper earlier where we apply now the same approach at the level of horn clauses, and we end up with horn clauses plus heaps plus the same invariants. So it's the same approach, but at the level of horn clauses. And one can also simply delete these constraints over heaps from these horn clauses to end up again with the constraint horn clauses. But again, you end up with a sound but incomplete set of horn clauses. So again, if you get an unsafe result, it's not really, you don't really know if it's unsafe or not. An example of this space invariance, I will now show the examples at program level rather than horn clauses, easier to read. Let's say we have some struct with two nodes, two fields, data and next. So it's just, we will construct a linked list using this. And initially we start with assigning null to some pointer. And while a non-deterministic amount of times, so this star means just non-deterministic, we allocate a new node. So initially A points to null, and then the node will have value 3 in this data field, and it will point to the original value of this A. So we are building nodes this way at each iteration. And in the end, after some amount of iterations, we will end up with something like this. Or we could just end up with A points to null if we did not iterate at all. And then later on, we are checking that we iterate again. As long as A is a valid pointer, we want to show that the data field of N is 3. Like, this looks like a super simple property to show. And this is a functional correctness property, right? I have to reason through the heap. And I have to say for all nodes reachable from this pointer A, the data field contains the value 3. But this turns out to be quite challenging for most tools. So you have to do some kind of, you have to infer this invariant, which is quantified, really. So this is tough to do automatically. So what we do instead in this invariant-based encoding, as I said, this is already existed in the literature in this J1 tool. You define a predicate I, so you leave this uninterpreted, and you just assert the current pointer and the current value of the node that you are writing to the heap. And then you can later on assume this. And maybe you can already see why this is incomplete, but in this example, since we have only one write to the heap, so we are only updating T at this line 10, this works. And now, it's very simple invariant can be expressed here that is not quantified. Basically, we introduced the heap invariant, saying that this I you can now replace it with n.data is 3. And this is, of course, sufficient to verify this property. So the tool has to infer a much simpler invariant than if you do not have this. And the loop invariant doesn't even have to mention, like only you mention this in I. Of course, this assert and assume, whenever you have an assume, you have to make sure that you don't assume a contradiction. So there are some correctness proofs involved here. But yeah, this is one way of doing this. However, that approach fails when you have, like, for example, something a bit more challenging. This example is, I think there should be n nodes actually, not n-1 nodes. But so we allocate some nodes using malloc, and the malloc actually writes some node with non-deterministic values to the heap. And then in the loop, as long as I is less than n, we allocate the next node, and then the current node's data field is set to 2, and then we move to the next node. So we build this list. And here the tricky part is after we exit this loop, we set the data field of the last node to 3, and then it points to null. So we have some amount of nodes, n nodes it should be, I think, with the value 2, and then we have the last node, the value is 3. And we want to verify this. And the previous approach fails in doing this. Like you have to, because the approach itself is incomplete. Like you cannot really distinguish between the different writes to the heap. And there are some ways to improve that encoding. But what we wanted is to start from a base that is both sound and complete. And then you can apply some optimizations to that and try to solve things, like improve solving from there. Yeah.
So when you assign the cur next to null, is that a leak?
When I assign cur next to
on line 10, because in the loop body you create a malloc, so that's a new object. But then in 10 you assign null, but you didn't free the previous.
I mean, here I'm not interested in like freeing. So I'm just building up. I'm not freeing anything. So just think of this functional correctness property. So memory safety is, but yeah, that would, I mean, this whole thing would leak. We don't destroy anything. But yeah, the last node was constructed, allocated here in line 6 in the last iteration. Or if this loop did not iterate, it would be this malloc, first one. And then we just set its values after the loop. So if n is 0, then we would have only a single node with the value 3. And if it iterates, and we have n nodes with value 2, and then last one is 3. So what we do in this work is
the second loop. What is it doing?
It's just iterating as long as like starts from the head. It iterates over this thing, and that just.
But just for showing purposes, because it's not really needed.
I mean, it's a property that you check, that you want to say that, okay, this, you have some.
Okay, that you did the allocation correctly.
Yeah, I mean, it's maybe not, something you would write in a real system, but if you want to, you could think of more common. Even these simpler properties are very challenging to verify.
Actually, it doesn't do anything. It just have assertions.
Yeah, it doesn't. It just checks, like inspects this. I mean, you can find many such examples in SVComp. Like, They're not from real systems, but many tools fail in these examples. And if you cannot even verify this, how would you even verify real systems, right? So yeah, one way to do this would be like you do shape analysis, and but all of those methods can be used. So one thing to understand here is that our approach is not like incompatible with any of those. So you can do shape analysis and add more additional information. But what we want is an encoding for the heap operations itself. Like think of this like a theory of arrays or heaps that you want a sound and complete decision procedure. Okay, so what we do here is we stay at program level first. We do some kind of transformation, and we add. We only make use of this uninterpreted predicates. We assert and assume predicates with. Do I have 30 minutes or 45? 12? Until 12:30, I think.
More 30 minutes.
Okay. I will probably finish earlier, but.
Well, no problem. You have the time you need.
Okay, thanks. So yeah, in this work, we go from programs to programs with uninterpreted predicates. And this is very easy to support these uninterpreted predicates just because.
Sorry, you have, I misunderstood my own notes. You have 5 more minutes.
5 more minutes?
Yes, but
okay.
We can adapt if you need more time.
Okay, maybe 10.
So the point is you explain whatever you need to explain.
Okay, that sounds good. I will then speed up slightly. But yeah, this should progress fast. So before I explain how we do this encoding, like the idea is to think of a heap trace. And so when you're executing a program like this, you can think of what happens on the heap, like a chronological order of operations. So you first allocate something and then you update. But yeah, let's look at this example. We start with line 2. We first allocate a node, and head is currently unknown. The cur is like it's not assigned yet. We didn't enter loop. I is star, and then let's say we set n as 3. So we will have 3 plus 1 nodes, 4 nodes in total. So once I allocate, this 1 here means the first address. So the green ones are the addresses, and then stars mean that I don't know what the data is and what the next field. So this blue is the node data field and green is the next field. And then I after enter the loop. Now cur is 1, it's pointing to the same thing as the head. And then I is 0, n is 3. And then I allocate, this is executing the malloc operation. I allocated a new node at address 2. So now I have 2 nodes, but both are uninitialized. And then I set the next field and the data field. So the data field is 2, but I set the first node, right? I allocated the second node, but I set the values of the first node. So this is setting the values of the first node. So this is not a new node, like just the trace, that the information that I have. And then I iterate again. Now cur became 2. I will allocate a new node with address 3. And then I set the values of the second node. So the second node has now data field 2 and points to the new allocated node. And if I keep doing this, I will end up with something like this. And here I will have 1, 2, 3, 4 nodes, and the last node has data field 3, and the last field points to 0. And now I will not change this trace anymore. So the heap is built. I will just read the heap, right? As you said, like we are not changing anything. And we want to check that this holds. And if you look at the assertions, this will indeed be a true program and a safe program. Now, we want to use this invariant-based encoding here. How we do that? First, we apply some kind of normalization. That is, we turn all operations like this allocation into allocs, writes, and this is the earlier program, just because it's a bit simpler to understand. So, I mean, this is a very mechanical step. We just turn accesses into reads and allocs and writes. And then we add some ghost variables to the program. So this is a transformation part still. And all our pointers are now integers. So they are not really pointers anymore. We use integers for the pointers. And we introduce some counts, etc. One thing to note here is that now my program must be deterministic for this to work. So I will use a trick here to quantify over all possible executions of the program. And I want all of those executions to only quantify over this value of this last address. So this is a ghost variable that I introduced, which is picked non-deterministically. And this will just scan through all the possible addresses that I will look at the program. But everything else is deterministic. That is, like we had the n, for example, that must be a program input. Like all the executions must behave in the same way. Okay, so once I have this program, I define read, write, and alloc. I don't show everything here. So this is, for example, my read method. This is one encoding that we have in the paper. And we now introduce this R predicate, and we assert and assume this predicate. And we show in the paper that why this encoding is correct. But let's try to understand how this really works. So it's a bit confusing, maybe. But okay, this last address is the ghost variable that we added that quantifies over all possible addresses. So this is a ghost variable. And initially, let's say this was, I mean, the verifier will consider all possible values for this. Let's say it considers this value 1. And here I have the solution for R. So the Horn solver or whatever solver I'm using needs to find the solution for this R. And if I execute this in my encoding with last address is equal to 1, so I'm writing some notes, etc. And if you remember, only in the read operations, I had this assertion to this R predicate. And now, and that assertion only happens when this last address is equal to the address being read. So here the address being read is 1, and the last address is 1. So when I execute this read, it will assert the value at this counter 1, and then it will, you can think of it like storing the value of this node. But because once the program is started, this value of last address does not change, I won't be adding any more. Like when, for example, the cur became 2, that doesn't affect when I read, nothing changes in the interpretation of R. And then once I go to the next loop, I will again go through this pointer. But okay, let's look at now another execution where now the solver has to consider where last address is 2. But the thing is, we are asserting this, when you're asserting a predicate like this in a solver, the solver has to consider all possible assertions from all possible executions. So you can think of this from the other execution where the last address was 1, we still have this information. Now, all of this is happening, you can think like while the solver is trying to compute the solution. And now, we will just add this second value, that is the second node, where the node is 2. So this assertion will only happen when the cur is 2 in the second iteration of this loop. Now we collected this one as well in this R. And if we keep repeating this, we end up with something like this in R. And this actually captures all the information we need. This captures this heap trace that we had, basically. Except we didn't really capture like the values that were allocated but not read. So here we are only capturing the values that we are reading. And you can see that this set of values is actually sufficient to verify that property that we have. And in general, a predicate, an invariant, so the tool using this encoding, we were able to infer this invariant automatically, whereas most tools in SVCOM failed. Only, I think, Predator HP could verify this program automatically. And that also fails when the shape analysis doesn't work. So it's a tool based on shape analysis. And yeah, you can see that for general, like for any n, this invariant, I won't spend time on this now, but so the first disjunct is basically this first three values, and then you have the second three values for the second conjugate disjunct. If you're interested in this, I think it's a nice invariant that's computed here. And once you have this invariant, you see that there are no quantifiers here. So this is the nice part, that you can verify this program using this invariant now. And yeah, since we are running out of time, I will rush a bit. But that was one encoding. We have other encodings as well. So you can customize these encodings. For example, you can change the read operation to not check memory safety, or you can check memory safety. You can use additional invariants. So in the papers, we describe like which advantages, disadvantages this might have. But if you don't want to check memory safety and only want to check the function correctness and assume memory safety, maybe you use another tool for that. This encoding actually works better than like checking everything. And then we did some preliminary experiments. We did use manual normalization, so that's why we don't have that many benchmarks, at least so far. And yeah, like these top 4 rows show the tools. So Tricera, CPA checker, and Zafer we used to over 20 benchmarks, and they could only answer 4 of them correctly, safe. And then, yeah, these are the unsafe benchmarks. So CPA checker actually, it's not so bad a job. But Zafer and Tricera were doing very badly for the safe ones, especially. Predator is quite good. And using these encodings with RWFun, actually, we were able to solve many benchmarks, at least, I mean, given that the number is that's not that many, but yeah, we could solve examples like the one that I just showed, which was beyond the other tools. Okay, yeah, I said that this works only with deterministic programs. We also implemented a way to, I mean, this is a mechanical thing that we can turn, like in SVCon, for example, you have programs like this. You have none that you can determinize this by, for example, using an array of values and then incrementing something, and you can consider these as inputs, and then you pass these inputs as arguments to the predicates that you have. And as conclusion and future work, yeah, these were preliminary experiments. We are now in the process of implementing the fully automated approach, which is almost done. So they are just final touches. And initial results are in this paper. It's under submission right now. And yeah, in the future, we also want to move this. So the idea is to approach this whole thing to the level of CHC, so that right-hand side arrow over there. So we go directly from CHCs with heaps into CHCs with standard theories. So apply it as a transformation at the level of form clauses rather than programs. Then you can just use like a Horn solver that does this, like use the theory of heaps, and you will benefit from this approach that we have implemented as well. And then once we have that, we got rid of this. We also have other approaches. I mean, this can easily be combined with other approaches like shape analysis, or, for example, program instrumentation. That was another approach to deal with arrays. Yeah, and that's my talk. Thanks.
We have had some questions on the fly, but if someone else wants to ask anything.
So the predicates you mentioned ranges over the allocated objects or over the reachable objects?
So
and is this not a state dependent? So the domain over which you implicitly quantify universally, doesn't it change while the program executes?
So for example, for this R encoding that I showed in the example, the predicates are only asserted in reads. So the writes don't really assert anything. They just store the value of the last written object, and that is sufficient to be sound and complete. I mean, it's sound, but it's sufficient to be complete. But it captures part of the trace that I show. It doesn't, for example, capture all the writes that are not read. So you only capture the writes that are actually being read because you are capturing the read size. But it's possible to also change this encoding. Like we have another one where we have a predicate that we are asserting at write sides as well. So that will capture different.
So your notion of completeness cannot capture, for instance, these allocated but not freed memory safety problems.
So for free, we haven't really thought of free memory freeing yet. So that will require another extension to this. So currently we have only read, write, and alloc. So you cannot check if memory is free. But we were doing earlier, I don't know if this will be applicable here as well, but you can write this special object, denoting that the memory is freed. And then you can check that, okay, after when the program ends, do my predicates heap all contain this default value. So that could be one way, I guess. But that's not still sufficient, like for all. For double free, it might work, like because when you're writing, you can check, you can read that location and see if it already contains that. But yeah, there are different ways of svcomp defines this when the program terminates, everything is free, but also it goes out of scope that it's free. This might be harder to check. I think it's called memory track or something. But yeah, we haven't explored this yet. This is future work. If someone wants to work on this.
Thanks.
Thanks.
More questions? Thanks, Zafer again.